Hello and welcome to Textbook Engineering Problem. We're going to be working out of Elementary Principles of Chemical Processes 3rd edition. We're doing problem number 2.31. 2.31. Okay, so I'll go ahead and read the problem statement. State what you would plot to get a straight line if experimental XY data are to be correlated by the following relations, and what the slopes and intercepts would be in terms of the relation parameters. If you could equally well use two different kinds of plots, rectangular or semilog, state what you would plot in each case. The solution to part A is given as an example. Okay, so for part A, it's given, but I'll show an example because they show the solution, but they don't actually show how you would do it. So y squared equals a e to the minus b over x. Okay, so we are plotting a line, and so our equation for a line equals, I'm putting these over bars and under bars so that we can distinguish the difference between this b and this b, and if there are any other duplicate m's or x's and y's. So this y does not equal this y, and this x does not equal this x, okay? So y equals mx plus b. That's our equation for the line. So in this case, what does y equal? Well, we say that they're taking this equation and they're making it look something like this equation, where they have a y term, an x term, and then a constant term, some sort of intercept term. Okay, so we need to take this equation and make it look something kind of like this, and then we can state what the y's, the x's, and the b's are, and all that kind of stuff. Okay, so let's go ahead and do that. We have y squared equals, we have this exponent term, so we need to get rid of that. And the way we're going to do that is we're going to take the natural log of both sides. So we'll take the natural log and get this function. Okay, and now we have something that kind of looks like this equation. So we could move the 2 out. We could move this 2 out of the y squared and put it in front and then divide. I'm not sure it's worth it. Did they do that in their example? No, I don't think so. So yeah, we'll just leave it as is, and we'll say our y equals ln y squared. Our x equals 1 over x. Slope equals this part that's attached to the x, which would be this part, which is minus b. Then our intercept is equal to this part, the part that's added on, so just ln a. Yeah, and that's what they have as they said what their solution is: construct a semilog plot of y squared versus 1 over x. So that's our y squared, 1 over x, or a plot of the natural log of y squared versus 1 over x on rectangular coordinates. Yeah, same thing. And then slope, correct, and intercept. There we go. Okay, so let's go ahead and do that for the rest of these. B, our equation equals y squared equals m x3 minus n. Okay, remember our equation for the line equals y m plus b. Okay, so looks like rectangular coordinates would do pretty well with this. So, and so we'd say y equals y squared, x equals x to the third, m equals m, and b equals minus n. Okay? And that is our equation for the line. So if we plotted, if this was our y-axis and this was our x-axis, and we took the data points and we converted all of our data points into x bar and y bar data, then this equation, if the data followed this model, would fit this line. Now let's do part C. 1 over, oh, they're making this complicated. 1 over natural log y minus 3 equals 1 plus a square root of x all divided by b. Okay. Let's see. We could probably just kind of take the inverse of this. Both sides, so now we just have the natural log of y minus 3 equals b over 1 plus a. No, we don't want to do that. Okay, so something we can do here is we can distribute this b to get rid of this division quirk that we have. Since it's all divided by b right here, it kind of makes it a little tricky to break it apart so that it looks like an equation for a line. So how I'm going to break this apart is I'll keep the y the same for now. And say 1 over b plus a over b. So a over b, I'm just going to say that equals c, because the constants are kind of arbitrary. So now I have c here, square root of x. Now we've switched that up, and we got something that kind of looks like a line, an equation for a line. So let's say y equals 1 over the natural log of y minus 3, x equals the square root of x. Our slope is c, and b equals 1 over b. Okay, c is equal to a over b. So now we have everything in terms of what they gave to us before. And we could easily plot this. We could plot this using the data. We could convert the data into, instead of y points, we could convert it into y points and x points, x bar and y bar and x bar points, and then plot it, changing these slopes, and then we could turn it into an equation for a line, and the data would kind of line up on the line like that. So just using rectangular coordinates. That was C. Now we're doing D. Y plus 1 squared equals a x minus 3 to the 3 inverse. Okay, how would I do this one? Well, we gotta break this up so that got something that looks like a line. And we can take the natural log, y plus 1 squared equals minus the natural log of a x minus 3 to the 3rd power. We can split this log of the product up into the sum of the logs. And then we can move this exponent down. Okay, now that looks a lot more like a line. Okay, so now we have our y equals L n y plus 1 squared. X equals ln x minus 3. M equals the slope, which is -3. And B, our intercept, equals minus ln A. Great, and we could just put that on rectangular coordinates and it would work fine, or we could put it on log plot and that would also work because we've got our x and y are both logs. So rectangular coordinates like this, or we could do log plot and just remove the logs as well. Okay. E y equals the exponent of a square root x plus b. I think it seems pretty obvious we want to take the log here because we're going to get rid of that exponent. So natural log y, get rid of that exponent and say a square root of x plus b. Hey, that looks a lot like a line. This is one of the easier to see ones. So y equals the natural log of y, x equals the square root of x, m equals a, and b equals b. F xy equals, oh boy, 10 to the a x squared plus y squared plus b. Okay. So I think it's obvious we want to take a log of this. So log of xy equals a x squared plus y squared plus b. And that looks a lot like a line. So y equals the log of xy, x equals x squared plus y squared, not b. Our slope equals a, and our b equals b. Great. Okay, so now we've got our equation for the line there, and we put those on rectangular coordinates and we should be just fine. Or you could use a log plot where x or y is on a log axis and x is not. And in that case you wouldn't use the log there. All right, so F, what are we doing? G. Okay, so y equals ax plus b divided by x, all raised to the -1 power. Let's do the log again. So we take the natural log of y, we're left with the natural log. No, let's not do that. Let's just flip the reciprocal here. Taking the natural log doesn't really get us anywhere, so let's take the reciprocal. 1 over y, this looks a lot better. 1 over y equals ax plus b over x. Yeah, I like that a lot better. That looks a lot like a line right there. We could multiply by x, or we could just kind of take as is. Let's multiply by x. Yeah, let's do that. Let's multiply the whole thing by x. So now we have xy equals ax squared plus b, and that looks a lot like a line. And we've just got one x term, one y term, and then a constant intercept off to the side. So that looks pretty good. There are multiple ways to do this correctly. By the way, if you found a different plot that works, all you have to do is have something that looks close enough to this equation, and if it fits the bill where you've got one y term, one x term, and one intercept or one constant, the only thing you need to be aware of is that this term, this constant term, cannot have a variable in it. It just has to be a constant off to the side. So this form wouldn't really work because we've got two x terms here, so we don't really have a constant term. Our constant in this case would have been plus 0. That would be our constant term. So in order to avoid that, I just multiplied by x all the way through, and now we have more of a constant term, even though it changes our y term to have an x term, or an x in it. So, and that's okay. This y term can vary with x and y. That's fine, as we saw in the last problem. So, or in some of these other ones. So y equals x over y, x equals x squared, our slope equals a, and b equals b. And that's you plot that on rectangular coordinates, and you're got a straight line there. All right, we finally reached the end of this problem. Thanks for joining me. If I made any errors, let me know, and I will put something in the comments or make a follow-up video or something like that. If there's problems that you need help with, just let me know, and I can try and run through some of the problems. Thanks for joining me today, and I'll see you in the next video. Thanks. Bye.